Welcome to the third main video in this course, ST2 on hypothesis testing. And today we're going to talk about power, sensitivity, and specificity and how to calculate them if you're doing multiple experiments. So what's worth maybe considering is this nice paper by David Colquhoun, where he considered this idea of using the p-value threshold of 0.05, which is a convention, but it doesn't really have any sound scientific basis. And in reality, due to issues with our imprecision in determining the null hypothesis and the use of incorrect models, and that can mean that we'll actually be wrong far more often than this. So it's actually a major issue. These underpowered experiments, they don't have the capacity to detect true effects and distinguish ones that are false positives, and therefore we can get this chronic problem of overestimation of biological effect sizes, and therefore you should actually use a more stringent p-value threshold if you're using that, and that's after multiple test correction as well. And also he also outlines why we should never also use the S word, because what we're really talking about is the biological effect that's of interest of us if we're looking at a biological hypothesis. We also have to bear in mind that part of this is caused by this perceived linear journey from data to results that we know is more meandering, but in reality, our assumptions about what we're looking at can bias our results, and these kind of can feed in. So we've in reality our web that looks like this, and that we have preconceived notions that will drive our results and affect interpretation of an objective analysis of the data. And we have to be very careful about that. So let's think about that in terms of this idea of power, sensitivity, and specificity. So these are two key criteria for determining how accurate, say, a comparison of different groups here. And we could be looking at an assay where we're trying to, PCR amplify a bunch of different samples, and we'll have ones that amplify well, given a particular primer target, and some that don't amplify well. So those could be ones, say, that we're trying to detect a particular virus that's present, where it is present, and we detect that it is present. And that would typically be the vast majority of our cases. And those are the true positives. We may get an issue where we get false amplifications, and those are type 1 errors, also known as false positives. So those ones where just something went amiss, and we got a false off-target amplification. The other issue is the ones that we miss. And obviously, there could be a range of factors, reagent preparation, a low initial DNA concentration at the start, or these sort of things that can lead to this situation, having false negatives, the ones that we miss. So those are type 2 errors. So we talk about type 1 and type 2 errors, we talk about false positives, and then also false negatives. And then also the ones that are true negatives as well. Those are ones that where there's nothing, that are negative control, for example, we'd expect that nothing amplifies there. And therefore, we can consider how our sensitivity is related to the true positives and false negatives. So that's these two ones. And our specificity refers to the true negatives and how that relates to the false positives. That's the true positives refers to our capacity to detect effects that are present. Our specificity is to discriminate from ones that are not present. So that's going to looking at the presence positive for that particular item, and the other one is looking at the negative. So we need a test that actually has both of these things: the sensitive to detect our effect, also specific enough to distinguish that from effects that are not actually relevant to what we're looking at. So we can think of the ones that are actually truly positive as the ones as the true positives plus the false negatives, and then also we have the negatives, which are the true negatives, but also the false positives as well, because they're not real. So in very simple terms, you can think of it like this, that a type 1 error is a false positive where you're telling a man that he's pregnant, and a type 2 error is a false negative. There's the ones that we miss that are actually positive, and that's like telling a very pregnant woman that she's not pregnant. So think of them in those simple terms. So that means if we miss pregnant women, that impacts our sensitivity, our specificity to distinguish that if we have, we're trying to identify a feature in a test, that we'll have ones that don't have that feature. So that's specificity. There are other metrics as well, accuracy and precision. Accuracy is the true positives and true negatives altogether, divided by the total. So that kind of refers to the mean. And then precision, we're going to look at this positive predictive value, which kind of reflects how good a test is in essence. That's the true positives related to the true positives and false positives. So this also relates to the false discovery rate, which you can see is there just the false positives over all the positives. So you can see that we're going to focus on the PVV, which relates to the false discovery rate. And specificity and sensitivity is something we can also apply in this work as well. So what we're trying to tackle here is this issue that if power is low, we want higher sample sizes, and that will mean we can detect real results and have higher specificity and sensitivity. And that will mean that the effect of false positives is lower. It won't mean that we've more accuracy, our biological effect may be truly present, but we'll have more precision in estimating and have a lower range of uncertainty associated with detecting that biological effect. If we have an underpowered experiment, our level of uncertainty will be extremely high, such that our result may not be actually meaningful. So what we can want to consider then is doing lots and lots of experiments and think about what fraction will we have real effects for, and how we can think of our standard statistical metrics of alpha, our alpha threshold, and then also our power, which is 1 minus beta. So let's say we do a bundle of experiments where we have 50% of them have an effect. So what we're saying here is that we're going to assume alpha is 0.05, just for example, and imagine this situation where actually 50% have a true effect. So these are actually positive, and these ones are, wrong way around. Positive in blue, and the negatives here on the left. That's an N for negative. And then if we have 100 tests in total, we might have 50 of each, for example. And then we might want to consider using this shaded area as kind of a measure of the fraction of experiments. If we have a certain level of a certain alpha, what's our capacity to avoid false positives? And then also what's our capacity to detect true positives as well on the other side, given our power. So therefore, if we think about having 100 tests, we can allocate the shaded areas in this way. So this is our alpha here. So this alpha is 0.05. So therefore, if we go over here, we have 50 tests that we're looking at here. So we multiply this 50 by our alpha value, and that will give us our fraction of false positives. So 0.05 by 50 is going to give us our fraction here. So we'll get 2.5 as our false positives, which is denoted by this area here. So this is 2.5, and these are our false positives. And that means, because we're using this dotted line as the break for the 50 and 50, that these are our true negatives on this side, which is the remainder, 47.5. And then on the other side, we have this is a function of power. So, oh dear, my pen is a bit wild. We have the other side, so we've got 50 here, and this is related to power. So if our power here is 0.5, that means we've got a 50-50 capacity to detect true effects and ones that are not true. So that means we get 25 true positives and 25 false negatives. There's the ones that we missed. That's given by the shaded area. So this is 25. So true positives. So we're just fitting in this area, and 25, and these are our false negatives. And that means we can get our PPV. So our PPV, remember, is going to be the true positives, which is 25, divided by the true positives plus the false positives. So that's where we get 25 over 27.5. And that corresponds to our value down here. Of 0.91. We can move on to further examples of this. So we can imagine a situation where we have done this multiple times. So this was our original instance here. We had 2.5 here, 47.5 here, 25, 25, and we apply different power values. And what's worth noting is that you see that the false positives don't actually change size here. That's 2.5, that's 47.5, that's 47.5, that's 2.5. And then what we see on the right-hand side is that our power changes. So power goes from 0.2 to 0.5 to 0.8. Remember, power is 1 minus beta. So our beta value changes each time. So in the first time, that means beta's 0.8. Then we have beta's, the next one is beta's 0.5. And then on the right-hand side, beta is 0.2. So for the first one here, power is 0.2, we multiply 0.2 by 50. So that's where we get 10 from, and 40. 25, 25, and they get 80. 0.8 by 50 is going to be 40 and 10. And that means we can get our PPV values. So this one, 0.8, corresponds to our calculation of 10 over 10 plus 2.5. This we had before, and this one is 40 over 40 plus 2.5. So you can see that's higher. So our probability value is higher than if we have more power as we expect. And what this means is that our probability of being true positives, if we test positive, is much higher here. So you can see how here, even if we have a sample that is positive, we have only the chance that it is truly positive if it tests positive is only 80%. Whereas over here it's 94%. So we can see that how our values have changed across here. In a more realistic example, we can imagine, let's say we have 100 tests here given by this area once again, but we use the same criteria and see what happens. So this side now is 90, and this side is 10. And we go through the same procedure for, so we have 90 by 0.05. So that will mean that this area here is at 4.5 for the false positives. And that's the remainder here. So we got 85.5. That's for the true negatives. And then here we have the two positives. So power is 0.5. So 0.5 by 10 is 5. And this is the remainder false negatives. So that's 5 again. So that means we can get our PPV is equal to 5 over 4.5, our false positives plus 5, which is where we get this value down here from 0.53. So even if something tests positive in this context, there's only a 53% chance that actually truly is positive. So you can see how when we actually apply this to more realistic scientific experiments, our capacity to detect things is very much a function of power, and that's quite important to note. But then therefore we can now go through the same procedure as we had as before. So this is what we had. So this is 4.5 and 85.5. This is 5, 5. So the true positives here. So this area, remember, is our true positives here. So in this side, we have the same values, 4.5, 85.5. This is our false negatives in gray. So this is now going to be 8 because our power is 0.2. And this is just 2. So that means here our PPV comes from 2 over 2 plus 4.5. Hence, this is very small. So even if you test positives, chances are still actually not even real. So this test is useless. This test is as good as a coin toss. And this test over here, we have 85, 85.5, 4.5, and this we have 8 and 2. So this is better, but it's still not great because you have 8 over 8 plus 4.5. So if you're in a lab and your true positives are only associated PPV of 64%, that may not be very, very useful for you in the context of your experiment. And that's why we want to calculate our PPV. So you might do many samples to determine what are the numbers that are true positives, false positives, true negatives, false negatives, to determine what PPV is present. We could then apply this in other situations as well. So we look at kind of epidemiological type data, but it can be very much applied to assay development or something like that. And therefore we can think about applying this elsewhere. So what we have this diagram here is imagine that we test many, many people. We're just taking 10,000 here as a starting point. If the prevalence of the feature, so it could be a disease, it could be we're testing a bunch of different samples where we expect to have 1% that have the condition or have that feature, have the whatever allele of interest. We look at how the ones that are either true positives or false negatives in this side. And then on the other side, we have the ones that are false positives potentially or true negatives. So if our sensitivity is 80%, that means we're allocating the 100 people that actually have the condition in this example, or 100 livestock that have the condition, to the true positives and false negatives. So that's where we have a sensitivity of 80%, which means we allocate 80 to the true positives and 20 to the false negatives. The same for the specificity. If the specificity is high, we can take these 9,900 people and allocate them to this groups where 9,405 are true negatives and 5% are false positives. So 495 are false positives. So you can see these specificity and sensitivity values are not bad. But what we work out is that our PPV is going to be 80 over 80 plus 495. So you can see here, our PPV is going to be very, very low. And even though the sensitivity and specificity may seem high here, they need to be much, much higher because the disease, the issue, whatever, is very rare. So it's not going to be useful. If we think about more common issues, so this could be looking at, say, 1,000 people who are the prevalence of, let's say, something like asthma or another feature is very, very common. Even with the same values, we will get a better capacity to detect true effects. So we'll get the same number of true positives, 80 here compared to the false negatives. So we have 80 and 20 false negatives from 100, 900 here. If we use an alpha value of 0.05, that means we get 45 false positives and 855 true negatives. And you can see here that our PPV is now improved. So 64%. But that test is still not really something that you're going to use more widely because the PPV is still very small. So therefore we need higher power to detect true effects. Another example we can go through is, let's say, virus antigen testing versus PCR-based tests. And these are just example values, and we're dealing with an issue that is 1% prevalence in each case. And we're going to compare and contrast two illustrations where we're doing a more sensitive specific test, RT-qPCR, where the sensitivity and specificity are 99%, or antigen-based test in this hypothetical scenario where the sensitivity and specificity are 70%, and we're taking a lot of numbers at the start. So let's work through this example. So we're starting off with that prevalence. So therefore we can calculate the prevalence of those numbers of people that fall into this category. So we're dealing with 49K of people that actually have the issue, and 4,851K that don't have this issue. And if our sensitivity then and specificity are both 99%, we can use these factors to work out the numbers that are true positives, false negatives, true negatives, and false positives. So that means our alpha value is 0.01. So that means our false positives then are going to be 485.1K. Sorry, 48.51K. And our true negatives are going to be about 4,800 and 2,490. So this is a situation where we apply to the whole population. Our false negatives are going to be, ones we miss are 490. Our true positives are going to be 48,510. So you can see here, if we do population-wide for a large number of people, this RT-qPCR, we're comparing our PVV, comparing our ratio of true positives and false positives. So even though this is highly specific and highly sensitive, if our issue, disease, or feature is rare, we'll find that our PPV is actually not very high. So our PPV is going to be 0.5 here. And we can work out as well the accuracy. So the accuracy is something we can calculate as well. So that's going to be the ones that are true positive plus true negatives versus all. And that's going to work out as 99%. So that's a function of specificity and sensitivity. The test is highly accurate, but a PPV is only 0.5 because of the function of prevalence of the disease more widely. If we look at this alternative, say we're looking at antigen testing, we go through the same steps here. So this is 49K. My pen is slow, so patience is needed. Or 851K. And then we're looking at the same thing, true positives. So this is our power in this side, false negatives, true negatives, false positives. Our fraction of false positives is going to be higher here because we've got 70%. So here we're going to get 1,504,000 approximately. This one is going to be about 3,396 approximately. Our false negatives are going to be 14.7K about. And then up here, our true positives are going to be 34.3K. So now we can see that we have something that is simply not useful. So here, our PPV works out as 2.333%, even though the accuracy as you can guess from above, is still going to be 70%. So if you change the values in here at a higher prevalence, those numbers would change, and you can imagine that the PPV would increase. If we increase the frequency of the disease, roughly speaking, the PPV actually would increase by about 10%, so it'd be more than 20%. So you can see how these are kind of related together. And therefore, we need tests if we're applying them more widely, but highly specific and highly sensitive. And of course, if we're looking at viral testing, it's more complex because we have to consider the time course of viremia over time from this kind of cartoon graphic, which is obviously not to scale. We'll have a period during which our test will be able to detect a true positive. We'll also have issues where or depending on the sensitivity of our test, we may have false negatives. And therefore, we might also have a true negative. And we also have this issue of our limit of detection depending on the viremia level. So of course, it's not very straightforward. But we can look through things more in more examples here. So here's another example where we have a test with 95% specificity and specificity on our left, with 400 people that have a disease that is 5% prevalence. So the ones that have the issue are shown red, and the ones without are shown blue. If they get a negative test, they have a chance of 0.3% of being infected, whereas the PPV here is only 50%. So increasing the specificity and sensitivity will combat that. If we look at a simpler test with 70% to 70% we had before, the PPV now is only 11%. So that's going to be quite low, and that's not going to be useful. This is another example here. This is about the high fraction of people that have 2 vaccine doses at the time becoming infected. But this is simply a reflection of the fact that many people have those 2 doses at that particular stage. So if you imagine that 92% of people fall into this category of being fully vaccinated, we can then apply the same logic to think about what's the prevalence of that among this group relative to the prevalence of that among the other group, and therefore look at the fraction that will likely present with the disease in this case, and go on to fit into further criteria. And therefore, we can look at the ratio between the different ones and work out how the prevalence is a major factor in determining what will happen next. So it's kind of worth kind of doing these flowcharts to think about what is going on. So that kind of concludes this portion on power, sensitivity, and specificity and how we can apply to different situations. Please see the next video to see more on this area.